Good afternoon, everyone. So let's start today's class. Now, in this class, we will talk about the axiomatic treatment of the utility. So let us revisit what we have done in the previous class. So in the previous class, we have shortly uh, we have seen brief introduction of the game theory, and we have seen that in the game theory there are basically three parts: classical game theory, behavioral game theory, and evolutionary game theory. And then we have talked about why game theory is a very important tool or very useful tool for representing a universal interaction. And by interaction I mean strategic interaction. And we have seen that I have give multiple example from ant to human corporate, that in these animals, in ants as well as in humans, we will often find that there are multiple examples which outcomes are not only depend on the not only depend on the one individual's action, but the individuals who are taking part into that uh, things, all interaction is important. So suppose there are multiple individuals are there who are doing a shared project. So it is not the only one individual action determines the outcome, but all the individuals who are take parts in that assignment, all of those role is very important. Now, and we have seen that such kind of examples we can see in every life. It means everywhere in our life, from ants to human beings. And we have seen that there is a very useful, elegant mathematical tool by which we can capture this aspect of strategic interaction, that is game theory. And to represent game theory basically nothing but it capture mathematical structure between the conflict and cooperation among various individuals. Now, where the conflict of interest comes at the first, the only interest come, and if everybody has some interest, then the conflict between their interests arises. Now, to model the conflict or to mathematize the interest, we need there are various theory which tries to mathematize the interest. But in the game theory, the founding pillar is the utility theory. First, von Neumann Morgenstern formalized the theory of utility. Now, what is utility? It, as we have told in the previous class, so utility, concept of utility is derived in the book of the theory of games and economic behavior by von Neumann and Morgenstern. That they derived this concept by giving an analogy from thermodynamics of the physics. So so if the interest is a thing which is feelings of human beings, suppose in the thermodynamics also it deals with the feelings of it starts with the feelings of human beings. So when we touch in some cold body, we feel coldness, and if I touch some hot body, we feel hotness. So how can we characterize this hotness or coldness that we feel? So these can be this question actually is resolved in thermodynamics. So how this question is resolved? By introducing a concept temperature. Now similarly, in case of preference or interest, von Neumann Morgenstern in their book, by the analogy of this thermodynamics, they introduce a concept called utility. And what is utility? Now that we will talk in this class, that we will learn in this class. So we will basically see the axiomatic treatment of the utility. So let's see. Okay, let me. Okay, so here we will see. Something. Okay, so there is something, some glitch is appeared, so wait. Let's resolve it. Now it is right in case. Okay, it is right now. Axiomatic treatment. So let me restart because it is not working. So let me be with. Sometimes restart this. Work. I guess it will work now. Axiomatic not working, so let's see. Okay, now it is work. I don't know why it is not working there. And axiomatic treatment of utility. So what do I mean by axiomatic treatment? So what do I mean by axiomatic treatment? Let me treatment. So by axiomatic treatment, I mean I want to predict the outcomes. Want to predict the outcomes from some simple realistic assumption. And what do I mean by that? So what do I mean by the prediction? Prediction is nothing but how a subject, how an agent, or how an agent choose a option if I present multiple options. So by prediction means what option an agent will choose if I present multiple options from some simple looking assumption. Now as we learned in the previous class, there are basically two parts. One is deterministic utility theory, and second is deterministic utility theory, or rather I'll say yes, deterministic utility theory. Another is stochastic utility theory. And the deterministic part was given by VNM, von Neumann and Morgenstern. So it is called the VNM expected utility theory. It is equivalently known as VNM expected utility theory. And there are multiple way to representing the stochastic utility theory, but in this class we particularly interest to present the stochastic utility theory present by Osborne and Rubinstein. Osborne and Rubinstein in the paper 1998. It is called utility of procedural rational utility. So let me first introduce the VNM, expected utility. VNM, expected utility. As we previously known that if I go back to the previous lecture, so where we end that decision making under certainty. So decision making under certainty and decision making under uncertainty. So decision making under certainty is a part of VNM utility theory. Now where we have said that it ultimately boils down to the maximization or minimization of some index function associated with options, and the main challenge that one finds there is to how to in general write this index function. Now we have faced the problem there is no general way to write this index function, but what one can in case of economical problem and evolution problem, one knows this index function, and basically these index function are nothing but the utility that we are talking about here. So first we will learn about the decision making under certainty. So this is decision and we have just hinted about that how one can in general there is a one systematic way to write utility or in that index function for is called the pairwise comparison. So it's called pairwise by comparison. So what do I mean by that? Suppose in front of a subject there are n options, a1, a2, an. Now first I will present in front of the subject two option ai and aj, where I can be anything between 1 to n and j also can belongs to 1 to n, and this I not equal to j, that means I will present in front of the subject two different options, and I will see that the subject is preferring either ai or aj. So the subject will either prefer or indifferent ai, that means these symbols is called, let us either ai is preferred over aj, So these can be written, or I will represent in mathematical symbol in this curly greater than, or maybe write it in greater than symbol. So AI is, so this is called, the AI is strictly preferred, or equal strictly preferred over AJ, or similarly it can also happen that AJ option, jth option, or AJ is strictly prefer AI. Or another thing is can be possible. So first, either this can be possible, or this can be possible, or another option can, another thing is possible also. So that individual may feel that he is indifferent between AI and AJ. So that means AI and AJ options are indifferent to the, are indifferent or different to the subject. So that means AI, so in the pairwise comparison, if I present any two among the n options, so these two options may be between, if I, when I present pairwise, suppose AI and AJ, then either AI is preferred over AJ, or AJ is preferred over AI, or AI is indifferent with AJ. So that means the, if I present in front of AI AJ, the subject will not mind to choose AI or AJ. He is actually indifferent between AI and AJ. He or you can say that agents or that subject equally like AI AJ. So this is called the, so this is called the completeness axiom. Completeness axiom, and it seems very natural, and this is called completeness axioms or completeness assumptions. So if I assume that my subject preference will be complete, that means in the pairwise comparison, in the pairwise comparison in the pairwise comparison comparison between AI and AJ, subject's preference between subject between AI and AJ will be either AI is preferred over AJ, or AJ is preferred over AI, or AI is indifferent with AJ. So then I will say that the subject preference completeness. And another thing is, so if I present three options, so which is also very natural. So suppose I present AI, AJ and AK. Now suppose that in the pairwise comparison between AI and AJ, AI is either greater or indifferent with AJ. First condition this. Second condition, suppose that with the pairwise comparison, in the pairwise comparison of AJ and AK, AJ is preferred or indifferent with AK, then the question is, can we say about anything between the AI and AJ? So this AI and AK. So can we say about anything when I will compare between AI and AK? So this is very intuitive, how we think that if AI is preferred over AJ and AJ preferred over AK, it is very natural to think that AI should be preferred or indifferent over AK. If the subject preference obeys this relation, it is called this preference is transitive between this pairwise comparison. So that means if when the preference is transitive, if I present the three option, and if I present in front of subject then AI and AJ, AI is preferred over AJ, and if I present AJ and AK, AJ is preferred over AK, and when I present AI and AK, you will find that AI is preferred over AK, then I will say that the preference among AI, AJ and AK are transitive. So this is called the transitivity axiom. So second is called the transitivity axiom. So among three options AI, AJ, AK, if AI is preferred over AJ or indifferent, or AJ is preferred or AK, then must AI must also prefer over AK. So this is called transitivity. Now there is a caveat. So before going to caveat, what is the implication of these two? Let us see that. Now from here you can see that it naturally bring us toward the real number. So that means these if I give an example, suppose the number 5, 9 and 20, you will see that so between 5 and 9, there is a relation, 5 is less than 9, and here 9 and 20, between 9 is less than 9 is less than 20, and among 5 and 20 is 5 is less than 20. Now this relation is also transitive. How we will see? So first if you compare 5 and 9, 5 is less than 9, and if you compare 9 and 20, 9 is less than 20, which actually infer that 5 less than 20. So this transitivity and completeness axiom, if some body's preference if some complies with these two axioms, then we can surely say that individual's preference or the individual's preference can be represented by the real number by associating real number with these options. So suppose there are A1, A2, N. So we can associate real number with this. Suppose here 1, 2, we can associate real number we will with the option. And how we will associate the real number? So we will associate a smallest number, smallest number to least prefer option, and largest number. So let me give an example. Then it will be clear how we'll keep this number. Suppose again I have 4 options: A1, A2, A3 and A4, and suppose that A1 is preferred over A2 and A2 is preferred over A3 and A3 is preferred over A4, and naturally the other relation will hold. So I will associate a number with 1 with A, 2 with A2, 3 with A3 and 4 with 4. Then you will see these numbers actually represent the preference. So if I say the utility of A1 is 1, utility of A2 is 2, utility of A3 is 3, utility of A4 is 4, you will see that the utility of A1 is, or utility of in the reverse order, let me do the reverse order. So U1 is 4, U2 is 3, this is 2, 1. Then you will see that utility of A1 is actually higher than utility of A2, which satisfy this relation. So I cannot imply both of either greater than or less than. So let me write this way. So utility of A1 is greater than utility of A2, or utility of A2 is greater than utility of A3, because A3 is 2, U2 is 4, and utility of A4 is greater than utility of A1. So that means by representing by these numbers we can associate the utility, and these utility are nothing but the index function that we are talking about. So that's how for if the decision making under certainty can be tautologically predicted if we know that among the preferences there are preferences follows these two axioms. One is completeness and second is transitivity. Then we can associate the real numbers with their options to represent their preferences. Now here is one property you can observe here. So instead of 4 I can write any number. Instead of 4 I can write 100. Instead of 3 I can write 5. Here I can write 0.01. Here I can minus 50. So that means only ordinal relationship method, only ordinal relationship is required to represent the utility. The actual cardinal number does not have the actual cardinal value of utility does not contain any information, but when I present a set of options and when I associate a set of numbers whose ordinal I can means that means that utility is not unique, so which means the utility this utility function is not unique, so not unique. So in any set of n number, any set of n real numbers whose ordinal relationship is same, they all can be used as a utility means utility for this n options. So that is for the deterministic preferences. Now let us not deterministic preferences, this is yes, this is all about the decision making under certainty. Now let's talk about the decision making under uncertainty, and which is very interesting. So decision making under uncertainty. Now decision making uncertainty means, now why decision making is uncertainty is important for game theoretical purpose. As we know, the game theory means, game theory is nothing but a model of strategic interaction. And what does the strategic interaction means? Strategic situation means when the outcome not only depends on your action, but also depends on all others action who involved in that task, As for an example, a group of forager ants are trying to subdue a larger prey. So when they can successfully kill the prey, when all the ants together attack this larger prey, then only this group of ants can successfully kill that larger prey and successfully take their prey to the nest. So this is a strategic interaction. That means strategic interaction naturally involves the decision of others. Now think about a situation when you have to, in a strategic situation, strategic situation, you in a strategic situation you have to take a decision when you don't know the action of others. A classical example of this situation is, suppose in your uh, in your college they your teacher gave you a share project. Now you and your friend are assigned you and your friend, or maybe you are new to the class, so you are new to the class, so you don't know any other individual in the class, so you and a random classmate jointly assigned to this share project. Now you have two options to choose one: either do hard work for completion the project, or do nothing. Do nothing and rely on the work of other person. And your opponent also have the same option. Sorry. So your opponent also has the same your opponent also has the same action like you, so that your opponent or your project partner has also two choice. One is do hard work or do nothing. Now since you don't know your random classmate, so you don't know that the classmate is lazy or not, or eager to do the project, so you have to choose a action independently of your random of your share mate, if your project mate. Now in this case you have to take decision. You have to take decision when the knowledge of the other other members action is knowledge is not present. Now here you see that your project is depend on whether or not that other individuals is doing what. So that means in this situation, this is a situation where where this thing comes, the decision making. Here this is a classical example of decision making under uncertainty. Now how one can decide whether or not to do which action to choose. Now if one way is that if I can express this uncertainty through probability, so there is a way is called the VNM utility. So if I can associate some VNM utility or some number associated with each action under that, if I know the probabilities, and if I know the utility, then if I only just maximize or maximize the utility, and I will choose, or that individual will choose those action which will maximize his or her utility. So our job is to find is there we can write such a utility for this uncertain condition. So let's see that if that individual's reference follows some axiom or assumptions, we can actually write the utility for that individual. So which axioms are is that? So let me present that first. So this decision making under uncertainty actually boils down to, formally we can write in this way, it boils down to the uncertain situation, boils down to lottery boils down to lottery. What does this lottery means? So a lottery means, suppose there are some options A1, A2, AR, and one lottery L1 means that an individual will get the outcomes A1 with probability P11, A2 with P12, and A3 with P13, and so on and so forth, AR with P1. So that means a lottery means nothing but, so there is some outcomes, and if I mix those outcomes with some probability, I will call that is a lottery. So lottery means suppose let me give a simple lottery. So suppose I will get 100 rupees with probability 60%. With 60% probability I will get back 100 rupees, or I will get nothing with probability 40%. So this is a lottery. Now the question is whether or not I will buy this lottery by this with some rupees, with some, suppose with rupees 50 rupees. So will an individual buy this lottery with 50 rupees? So this is the question here. Now the first axiom which we need, that is called the reduction of compound lottery. Reduction of compound lotteries. So that means if I a complex lottery, then according to the probabilities law I will reduce this complexity, and with and I will reduce this complexity using the probability calculus. So let me keep this, let me state this. So state that any compound lotteries, any compound lottery is indifferent to a simple lottery with A1, A2, AR prizes and their probabilities being computed to the ordinary calculus. So let me give you that test what does this compound lottery means. So here this I have to define what compound lottery means and what these A1 A2 basic outcome means. So suppose a lottery, suppose L1, L2, LS are S simple lotteries. This is called simple lotteries. Why it is called simple lotteries, I will see that. So we will see that why this is called simple lotteries. So simple lotteries involve prizes A1 to AR. So which lotteries involve these prizes as A1 to some probability combination of A1 to AR is called the simple lotteries. Now A1 with what probability? A1, suppose lottery LI is defined as, so LI is defined as that in LI A1 prize will appear with probability PI1, similarly A2 will be PI2, and similarly AR will be PIR. Now what is compound lotteries? What is an example of compound lottery? Compound lotteries if Q1, Q2, Q3, QS are the probabilities. So basically compound lotteries means, so compound lottery means a lottery whose prize is a lottery. So a lottery whose prize is a lottery is a compound lottery, whose prize is not some basic outcome A1 A2, it's another lottery. So suppose, give an example, so suppose there is a lottery, a compound lottery with Q1, with suppose with Q1 probability, with Q1, a example of compound lottery with probability, okay, let me write in this way, so L1, L2. Compound lottery means the lottery whose prizes are L1 lottery, L2 again a lottery, and LS a lottery. So a compound lottery example is a lottery whose outcomes are L1, L2, LS with what probability? Suppose with probability Q1, with probability Q2, with probability QS. Now this axiom says, so any individual, if I present a compound lottery likewise these like this, that individual can generalize this or in more technical term, individuals in front of individuals, this lottery is indifferent to a lottery whose outcomes are basic, involving basic A1, A2, AR, and with some. So for an individual, if I present this compound lottery, that individual's preference of this lottery is indifferent with a lottery, simple lottery. With a simple lottery means whose outcomes, in whose prizes are A1, A2, AR with some probability, suppose P1, P2, PR. Now how this PR, P2, P will be calculated? It will be calculated according to probabilities law. What this probability law says, that what is the probability? So if Li, if in the lottery Li, the probability of appearing AI is what? It's nothing but P. What is the probability? probability that in the lottery LI the prize will be AJ is nothing but PIJ. Now in the compound lottery what is the probability that this LI will occur? The probability LI will occur the compound lottery, that is QI. So that means in according to the probability law, since these two are the independent event, since these two lotteries are independent, what is the probability that in the final outcome or the final prize of the lottery, that AJ will come and that AJ will correspond to the lottery LI, that probability will be QI PJI. Now AJ can be occur in every lottery, in every I. So if I summation over I will get PI. This PI will tell, according to the probability, this PI will tell that what is the probability that in the final prize I will get AJ. This I equal to 1 to S, because there are H such lotteries, and in every S lotteries that AJ will appear with some probability. So that means if I follow the probability calculus, I will generalize the compound lotteries into a simple lotteries, where I will say that in my simple that compound lotteries outcome will be with probability PI. I will get the outcome AI. What will be the PI? PI is nothing but Q1 PI into 1. The probability in the compound lottery L1 lottery will win, into the probability in the L1 lottery that A1 will win, and similarly Q2 so if it is so, then I will, and for if I present a compound lottery, it will be indifferent to a simple lottery. So if this way subject calculate, it is called the that means if the subject can reduce the compound lottery in terms of a simple lottery. Now this is not also, although it is look very apparent to us, but it is not quite apparent, because in the real world, when you will present this lottery, that an individual not always remain indifferent between the compound lottery and a simple lottery, because we are missing out here some terms. So what we will always see in observe or see in the real world is called that joy in gamble. So some people get joy in gamble and also feel thrill in atmosphere of game. And also pleasure of suspense. For these cases, maybe that compound lottery cannot be reduced to a simple lotteries, and for that case these uh, this methodology for calculating the utility for uncertain event is not valid. Let us go toward the second case, is called the continuity. Now another thing which is very crucial in case of von Neumann utility is called the continuity axioms or continuity assumptions. What it says, suppose I know according to the preference, so let us assume that thing, that if I present to the subject this A1 to AR, the most preferred is A1 and least preferred is A2, least preferred is AR. So in this way the basic outcomes, the preference of the basic outcomes is this. In this way, if I present these outcomes to the subject and pairwise compare that, the subject's preference will be like this, then I can formally introduce the continuity. Suppose that each prize is each prizes, that means A1, A2, AR, each prizes is indifferent to some lottery involving just most preferred A1 and least preferred AR. So that is to say there exists a number UI such that AI is indifferent to lottery UI A1 comma 1 minus UI AR. So this is called the continuity principle. So we can write that this lottery in this way, AI tilde is a lottery which is with UI probability I will get the price A1, and with 1 minus UI probability I'll get the price AR. Now why this assumption or this axiom is quite feasible, so let me explain. So suppose that since we know that this AI is in between A1 and AI, so AI means A1 is, if I present A1 and A1 will be surely preferred over AI, and if I present AI and AR will be preferred. Okay, I write it in the wrong way. I should write in this way. AI is preferred over AI and AI is in between. So suppose I make a lottery with this number, 0.99%, okay, with 0.99 probability I will get a prize A1, and with 0.01 probability I will get the prize AR. So obviously, since suppose let me give an example with real money. So suppose A1 is corresponding to 1000 rupees, AI is, A1 is 1000 rupees and AI means some maybe 10 rupees maybe, or 100 rupees maybe 100 rupees, and AR is 10 rupees. Okay, now I am making a lottery that with 99% of chance, or with probability 0.99, I will get 1000 as a prize. I will get 1000 as a prize, and with 0.01 probability I will get 10 rupees as a prize. Now obviously this lottery will be preferred over a certain outcome, 100 rupees, or maybe let be it 20, or maybe 15 rupees. So it is obviously one individual so it may happen. So for me, if I were the subject, then I will obviously prefer the lottery over certain 15 rupees. Now this is the one case. Now anyone present some lottery like this, so with 0.001 probability I will get 1000 rupees, and with 0.999 probability I will get 10 rupees. Obviously I will choose certainly 15 rupees over this lot. So there is a range of probability. This is nothing but UI. So we will always find that if I vary this UI, sometime you will find that AI tilde is preferred over AI. So that means this lottery is preferred over AI, and in some range of UI you will find that AI is preferred over AI tilde. Now from this experience we can certainly say there will exist some UI where this lottery, this there means so I am saying that, so since the preference is changed in this way, so let me rewrite it again. So okay, so since there will be some UI for which certainly this lottery will be preferred over AI, and if I increase the AI, okay, let me represent in this way to clear what is the UI. Lottery A1, in the lottery I will get A1 with probability UI and 1 minus UI with probability 1 minus UI, I will get AI. So obviously if I increase UI, if UI is nearly 1, then this lottery will obviously preferred over AI. And now if I start to decrease UI, and after some UI that preference will flip, because after some UI if I decrease, the probability of getting prize, highest prize is decreasing. So after some UI you will find that your prime, right, your double prime, suppose that after some UI you will find that A1 comma 1 minus UI AI is not preferred over AI. So that seems that there will be some UI for which AI and AI tilde, that lottery is indifferent. So this is the in general statement. So you will often find that this statement does not hold with real world example. So let me give an example of like that. So obviously for any agent, $1 1 rupee is preferred over 1 paisa, and 1 rupee and 1 paisa obviously preferred over death. Now if I say that, now according to, if the continuity holds, if a continuity axiom holds, assumption hold, then that means any lottery, so you will find that I will find the lottery, I'll obviously find a lottery between 1 and death, such that 1 paisa will be indifferent with the 1 rupee and death. So this is obviously no one will be indifferent with that, because if some lottery offer death with some probability, any individual will not be take that lottery for any price. So that means that apparently seems like that this continuity principle does not hold. However, if you see that this is not quite true here, because the death and rupees 1 is means not in the same footing, so the comparison and the preference is not making sense here. So that's why this is not logical to represent lottery with 1 rupees and death. So that's why it is not quite true that this kind of situation. And secondly, that if I also, as we have seen that in the previous case, that if we don't have that only continuity principle, then also we can write the utility. As we know, in that case the utility will represent the decision making under certainty. So this is the third assumptions. Now there will be another 3 assumptions is there to reach to the VNM utility. So I will introduce those concepts. So let me introduce the another assumption, which is called the independence of irrelevant alternatives. Then I will stop this class. So this is called IIR, or it's called independence of irrelevant irrelevant alternatives. Independence of irrelevant alternatives. Independence of irrelevant alternatives. Now what this means? So this means very simple. So in any lottery L, AI is subs. So that lottery that we have discussed in the continuity axiom, so that AI lottery is substitutable for AI. Since AI and AI tilde is indifferent, so it doesn't mean if I include another options with AI, then also AI and A tilde will remain indifferent. So substitutable for AI, so that is, so in a lottery that P1 A1, P2 A2, that PI AI, PR AR. So if I put irrelevant alternatives, that with probability A1 P1, with probability A2 P2, with probability PI with probability PRAI, it doesn't matter, since PIAI is PI, since AI is comparable, AI is indifferent with AI tilde. If I also present PI A1 P2 A2, these are the irrelevant alternatives, PI AI tilde PR A. So this lottery and this lottery is indifferent, and indifferent because AI is indifferent with AI tilde, irrespective of the all the other alternatives present here, all the other alternative as a price present here with some probability, those alternatives are irrelevant. So these from um, the relation that we get from the continuity axiom, that the indifference relation uh, remain independent of the irrelevant alternative. So this is another axiom, fourth axiom. So there are, in the next class I will present I will present that another two axioms, and I will also present the expected utility and its property, its linear transform property, and then I will present, then I will teach, and I will then I will introduce the concept of stochastic utility, which is uh, first first coined by the Osborne and Rubinstein in the paper 1998. So that's it for today's class.